Chemistry topic by topic. In our last video we had a look at NMR, and what I want to do today is to try and have a look at the previous video of NMR, the one before that of IR, trying to put them all together and see if we can actually solve some problems. So in a typical question in the paper you'll be given an IR spectra, an NMR, proton and carbon spectra, maybe a mass spec as well, and you'll be asked to, well, identify, can you work out what the substance is? So with my guest, Paul Russell, my son, who's going to come in and perhaps help us as we go along trying to explore what we're doing, we're going to have a go at seeing if we can solve a few of these potential problems. So let's have a look at the sort of thing that we might be wanting to have a look at. And here I've got a series of spectra we've got, and these are from Chemistry, University of Calgary, California, and we've got various bits and pieces. We've got here in this one we've got a mass spec, I think. No, not mass spec. We've got different ones. We've got IR, we have got mass spec, which is this one, and then we've got carbon NMR, and we've got proton NMR. So let's see if we can look at these and see if we can work out what we've got. So our first place normally when we want to go and have a look at one of these is to go and have a look at what I would suggest is mass spec is the first one to sort of start having a look at. So if we look at our mass spec, and this is the one that we've got to try and look at. I can make it a little bit bigger, but it doesn't seem to do what I want. So here we can look through here, and I see we've got a number at 72. So that's telling me that we've got probably a molecular weight of 72. Okay, so what else can we do from here? Well, that's enough of that one. That's going to probably help us initially, so let's just put that one to the side for a minute, and what we're going to do is have a look at the IR. Now, what does the IR tell us? Well, I've got some big peak here. This is at 1700, just a bit more, maybe let's say 1720, and I can have a look up in my little book. I've got a little booklet of my numbers to see what we've got for IR, and we can have a look at some things for IR, see what we've got, see if that's any sort of help. This is single bond stretching. We might have other things that we can have a look at. So we're looking at something at around about 17, I said it's about 1720, and 1720 could be something like down here. I could have something like CO bond, could be a C double bond, C bond. We're sort of looking at what things might be possible looking down. You know, sort of 1720 saturated ketones are looking sort of likely. So it may well be we've got a C double bond O. Well, it could be. Let's see what we could actually disprove with this, because we've got lots of numbers. So we also might look to find perhaps an NH group. Now NH groups are going to be a couple of places. We'd find if it's going to be an NH round about 1600. I went the wrong way, caught everything. So about 1600. Don't have anything here at 1600, so it's probably not going to be an NH. NH would also be around about 3200, and OH at 36 as well. I'm not seeing much at that point, so it doesn't look like I got an OH. It doesn't look like I've got an NH. Carbon-carbon double bond is another choice that I can have. Carbon-carbon double bond. They're around about 1600. That's not there. So I think I've got a C double bond O. So looking at my infrared, it's looking like I've got a C double bond O. I am fairly certain I haven't got an OH. I'm fairly certain I haven't got an NH, and it doesn't look like I've got a C double bond C group either. So I've learnt more what isn't there than possibly what is there from the IR. I've looked and seen that we've got this C double bond O. Okay, so let's see what else we can have a look at, and I'm going to have a look at the carbon 13 NMR. So let's do that. Let's take this carbon 13 NMR. Right, I've got 4 types of carbon. Okay. Now, what might they be? Well, I've got one really way off here, up at about 210. And I know from looking at my carbon NMR at around about sort of 210, it actually means something to me that I've got something there at around about 210, and that normally suggests that I've got here, it said something in the region of a carbonyl group 227 to 154. It's looking likely that it could be a carbonyl group. So I know it's not some of these other ones, they're in the wrong place. So carbonyl group seems to be confirmed. Then we got 3 other carbons. This is at 37. I know that looks more like 40 to me, so it looks like I got one about 40. I was reading it round the wrong way. So that looks like about 40 to me. We've got another one somewhere about, I know that's looking about 30, 33, 34, about 34. And I've got one about 12. Trying to sort of guess what they are. Okay, so 3 different hydrocarbon environments. Okay, so our next choice is to go and have a look at this one, and here we've got, perhaps I won't move it. No, I won't move it. There we are. So what have we got? We've got 3 different environments. I've got first of all 2 different heights. Let's look at the integration of these, and it says we've got 2, 3 and 3. Okay, we've got down here a triplet. Now, thinking of a triplet, that looks like I'm looking at something like a CH3.
So
my son's looking at me. Yep.
So the what you're looking at there with the integral of 3, you're looking at a proton or a group of protons that are next to a CH2 because of the n+1 rule.
Okay. So then, by that argument, then, if we look at this single singlet,
so that is a proton. That is 3 protons. A proton.
So CH3.
So a CH3 that is next to a lone or a actual lone hydrogen, or they've got nothing next to it, because the n+1 means they've got nothing coupling and they're only producing a signal of 1.
Okay, so that suggests then a CH3 group by itself.
CH3 group by itself, and then finally you've got this next one, which is looks like
a quartet.
A quartet. It's 4. So using the n+1, a quartet, which is 4, so n+1 equals 4, so that means n equals 3. So that means it's a proton group that's coupled to 3 CH3s. So that is, that's coupled across. So it's the 2 N ones are coupled together, because that makes sense, and then somehow you've got the middle peak is separated from itself.
Right, okay, so let's see if we can try and summarize some of those facts and see if we can write some of them down. So I think I've got a C double bond O group, so let's summarize there. We've got, I'm just moving the tables out of the way, we've got a molecular weight of 72. Now 72 gives me a hint before I even start that means I've got about 4 carbons. 4 carbons is going to give me 48, and if I've then got an oxygen in here, that's going to add on a 16 to that, so that's going to sort of take us up towards the 72. So it's, I don't think I would actually manage a 5 carbon there.
Well, if you can try a 5 carbon,
but
that's adding another 12.
But it doesn't look like that's going to fit from this carbon NMR.
So
Looking at the carbon NMR.
Look at the carbon NMR.
The carbon NMR's looking like we've got,
which is this one, which is
we've got 4.
So that means it has to be 4. This is the whole point of.
So we're looking at our 4 carbons.
We've got 4 carbons. So
and we've probably got a carbonyl group.
So carbonyl group, and then you've got 3 others, which is fine.
So the hydrogen NMR is giving me an idea that we've got a CH3 by itself.
A CH3 by itself.
I've got another CH3 which is attached to a CH2.
And that CH2 is coupled to a CH3. So those 2 are next to each other.
and then if we've got a carbonyl here as well, then I'm reckoning on a carbonyl coming in something like this. So my initial guess could be that. So that's going to give me 4 carbons. That's going to give me 1 oxygen, and then we're going to have 3, 4, 5, 6, 7, 8 hydrogens. So we've got
does 40 plus 48.
48 plus 16 plus 8, which is 72.
And we can check that answer if I find where you've hidden the bloody thing.
I didn't put it up.
Go to solution. Right, so let's go read through the solution.
Right, okay, so let's find the solution here. So we're not far off doing this. That we actually managed to work out molecular weight 72.
72, that's good. We show you've got a carbonyl there.
We couldn't see other things.
There is none of those, and there's none of that, which is at those meter. So you got
Carbon
4.
13. I don't know if I agree with their numbers, but that's what they say they are.
You've got those things, which is fine, and you can see there is that isolated, which is only n plus 1.
And we worked out they had an isolated CH3 and a CH2 CH3. So putting all that together, we had an aldehyde or a ketone. Now I went for immediately a ketone, and the reason I went for a ketone was I had 2 lots of CH3s, which suggests I didn't probably have a CHO at one end.
Yeah, that's fine, yes. So there you go.
But they said you could rule out now the aldehyde, because on the Proton Nmr we didn't have a peak, which we didn't look for, and so there we've got butanone.
Yeah.
Okay, so we've managed to survive one of these to see that we can actually work out how it works. So let's just go and choose another problem, and we'll see if we can go through and work out the logic behind this and see what we can work out. Okay, so we're going to have a look at our second problem here.
Right, so you started off in order they give you, which is mass spec, IR, whatever.
Yep.
Right? Now, that's fine and all, except you really want to get down what your functional groups are. And that's the first thing you actually do. Because knowing what's the functional groups, you can then confirm those in the mass specs. These all, but without knowing what you've got, it's sort of a bit nuts. So let's here look at this IR spectra. So it's a bit muddy in the wavelength, but you can see sort of you've got some broad peaks happening here. You've got definitely a sharp peak here, and then you've got some things happening, and then what is known as the fingerprint region going this way.
Right, so what we want to do then is see if we can have a look at what we've tried to get. Okay, so IR, you've got that really wide peak somewhere around about what I'd say about 3.3, about 3.3,
3.4,
3.3, 3.4.
Yeah.
Okay, and if we get our tables out, we can have a look at those, and that I'm cheating because I know what this is actually looking at, because I've seen this one so many times before.
Yeah, so 3304, which is down here approximately. So this is 3304. Oh look, it's this one here, which is this one, which is
It's a broad
peak, so it's an OH.
So this looks likely an OH. And we've also got that big one at about 3000.
It's got 3000. Now you can cheat at the 3000 because the 3000, if it's above 3000 at this point, it's aromatic, but if it's below, it is what is known as a carbon hydrocarbon chain. So you can immediately rule out it's aromatic, which is fine, and it's a carbon chain. So you've got
So we've got a carbon chain, we've got an OH group in it.
So you've got a carbon chain, so this is basically CH trees and lots of different CH trees there, and that's an OH.
Right, now if we've got a C double bond O,
so
because it could be, I'm thinking now it could be a carboxylic acid.
So we will have to look and see if there is a C double bond O.
So a C double bond O is going to be coming in at triple bond, cumulative bonds. I'm just looking down through your tables here. It's going to be round. We'd also have it round about where the amides are, aren't we? We're going to have it all there. It's going to be.
But what you actually look up is here. It's lovely one of these. It's this one. Ha!
There we are.
I'm just scroll from my picture. It's that one there. Unsaturated aldehyde and ketone. Right, and you're looking at it somewhere in these values, but
we haven't got one.
If you look at the spectra, so that will be around here. It'll be peak here. There's nothing, absolutely nothing. So we can confirm there is no C double bond O. And secondly, the next one you also look for is the C double bond C, which is 1600. Yeah, possibly is something there, but not fabulous peaks which you've got here, which you pay more attention to.
So we're looking at some sort of, probably some alcohol here of some sort.
It's an alcohol, or it's
something like that. Yeah, we don't know yet, but it's looking like an alcohol. We're looking at this saying probably not with a double bond, but probably a straight chain.
Right. So now we know we're looking at. Now it's to determine the chain length, which is the mass spec. So let's just open up the mass spec, and what you can see here is that you look at the molecular ion is
60.
Well, 60. Oh, you've got a little tiny peak here. That's your N+1 ion. So the molecular peak is 60.
Okay, so we've got.
Knowing that you've got an OH from 60.
So let's write a few facts down to start us off.
So we got.
Molecular weight 60. We know we've got an OH group.
And that is 17, so you can cheat and do 60 minus 17.
Yep, okay. So that's going to give us 43. Now, if that's 43, that's going to suggest how many carbons it's going to have.
Well, you could do.
I would
three.
guess.
You could do 3 because
I guess 3 carbons is a good place to start.
3 is 36.
So that would be a place to try and start here. I reckon that's probably a good place to start. So that's 36.
So plus the carbons, so that's what you're doing. That's another 6, 6, and 3, 6. Possibly a 2. So there's another 8. So 36 plus 8 gives us. Ooh, we have a problem.
Not quite.
Not quite. So there's a bit of something wrong with the carbon chain. There's something.
So there's something. Well, let's have a look. So if we're going to go and have a look at what the number of carbons are, then we want to go and have a look at the carbon NMR. So if you just call up the carbon NMR.
I can.
And we've got 3 there.
So that's confirmed the mass spec. It's all confirmed we've got that.
So what I've done here, then I tick my
3 carbons.
3 carbons. We know we've got 3 carbons. So next, I think it's the Proton Nmr, isn't it, to go and have a look at that.
So now we look at sort of where the these.
Oh, you want to look at where they are? Okay.
Yeah, just You can tell this is further away. It's more electronegative. So this is one hydrocarbon. This is another hydrocarbon, and this is a third hydrocarbon.
That's about 70. That one,
about
isn't it?
70. Usually
So,
70 is a indication. It's you know, there's a carbon there, but I don't think it's really that implicit. But these two are definitely part of the hydrocarbon chain. They're the ones surrounded by the hydrogens.
so they're almost certainly the CH3 and the CH2s, possibly.
Or CH3,
Could be, yeah.
Could be. So
Yeah.
there are two hydrocarbons here, and this is just a carbon on its own. We
So
reckon, or
possibly with
CH, there is something funny about this carbon. This is a carbon that will tell us everything.
So let's now go in and have a look at that and see what we can actually find.
So now let's move on to the proton.
So if we have a look at the Proton Nmr, this
Proton
will tell
Nmr,
us
right.
quite some interesting things coming up here. So 4 peaks.
4 peaks. So there's 4 different proton environments.
So we know we've got 4 probable proton environments, because if we've got 3 carbons, then possibilities are something like we've got a CH3 group, we might have a CH2 group, we've got an OH group, and then we've got a C, maybe H group.
A C H question mark, yeah.
Yeah, definitely a question mark on that to have a look at. So can we have a look at these in more detail, see what we can find out?
Right, so let's start from one side in. Let's go for this one, which 3.5, 3.6, that sort of number. Right, it's a triplet.
Okay, and an integration there, it's told us it's got 2.
Integration of 2, so it's a triplet, so that means it's n plus 1 is of 3, so n plus 1, so n is 2, so
It's a CH2.
that's a CH2, and it's so that is next to a CH2.
So we know we've got a carbon next to a CH2, and
Or we know that 2 protons are next to a CH2,
right.
which brings in sort of.
So that's almost confirming what we'd expect.
So
this one's in the middle.
So that's confirming there's a CH2, but it's saying there's 2 other protons. It's seeing there's 2 other protons next to it. Right. Then we move into this integral 1. Well, it's n plus 1.
Isolated.
So that's isolated. So that's definitely the OH.
So we can tick that one off as being the OH. So that's our singlet. Okay. And then if we look, oh, now that's
1, 2, 3,
multiplet, I would call that one.
Well, you got 1, 2, 3, 4, 5, 6. Yeah, won't panic. But the integral value, so integral value of 2, but is that 1.6 or 1.5? It is 1.6 over. It's not really.
Your gut feeling was right. It was just a bit more than 1.5.
Bit more. You know, it's not 1.7 because 7's in the middle there, but it's more that way. Anyway, so it's about 1.5. Integral value of 2. That tells us it's 2 protons in that environment. So, what is producing a multiplet? Now, your problem with multiplet is how do you calculate the n plus 1? And the answer is you cheat and you go 1, 2, 3, 4, about 4, 5. You basically are just calculating how many peaks you can see, but you figure from, pinch of salt. You don't panic about the n plus 1 more. You work everything out around it. So,
Yeah. Okay.
Anyway, so back to this. You've had a panic, and that means, well, it is an integral value of 2. So that means this one is a CH2, carbon, that's bonded to lots of things. So that means it's definitely in the middle.
In the middle. So we've got a CH2 in the middle. And
so there you go.
There we are. So we've got a, which is what we would expect. We've got a CH3, got a CH2 in the middle. We've got an OH. Let's worry about this funny thing.
So now we've got integral value of 3. about 1, but not really. It's a bit below 1, so 0.8, 0.9. Integral value of 3, so there's 3 protons. It's a triplet. N plus 1 equals 3, so n equals 2. So it can see, it's a CH3 because of the integral that can see a CH2. So that's that terminal environment, and it's at this end, so it's a low away from the OH. So you can definitely say you've got a CH terminal CH3.
Okay, so I've got a terminal CH3, I've got a middle CH2, we've got a CH almost certainly, and
now,
it's probably coupled to the OH.
If you're looking at the data or this mass spec, you can see this integral value of 2. So we can do 3 plus 2, 1. That means that carbon, this one here, has to be CH2 because the integral value showed it was 2.
So we had a question mark on that one, what it was, and we're fairly convinced now.
Fairly convinced the integral value is 2, therefore that's what it gives. Right.
Okay, so let's see if we can try and summarise what we've actually found, because it's looking to me, looking at this, that we've probably got something really quite simple as CH3, CH2, CH2, OH. So I'm going to reckon on this being propan 1-ol.
Right, okay. So if you go over and we hit the lovely solution and we read through. So here's the data, triplet multiplet, there you go. And slow it down. And we have propan 1-ol. And you can check that you had that 6 lines. This CH3 here, or was this proton was coupled.
It's going to have the 6 lines.
It's going to have 6, it's 2, that's 3.
Because there are 5 neighbours, yes. So that's what we've got.
So that's no problem, that's quite good. And it, you know, you can see. So yeah, so absolutely right. And the lone OH there, we could pick that out, no problem.
Right, so our next job then is, let's have a go at another one of these. We'll just try another one just to see what we can actually achieve with this. So if you want to choose another problem, we'll have a go at that one and have a look. Right, so you've chosen another one. We're going to start with
we could do number 3, or we could go bold, or we could go to 4.
Oh, sounds quite exciting. Yes, we can.
Right. So, right.
Try that one. So let's. You suggested starting with the IR again.
You start with the IR just to see what you've got, just to play around with everything, and the screen's gone blank. Ooh, fun. Let's try that again. No, it is just going to be blank.
This could make our life fun trying to work this one out.
Let's see if I can just. All right, maybe we won't do.
We're going to try and do this one without an IR. That should be more fun.
Well, let's skip over.
Or skip the next problem.
We're going to do problem 5. Just see an IR. Oh no. All right, they've all gone a bit dodgy. Let's see if any others. Nope.
We're just having a problem with the IR here. We had a few problems with the computer, which is why we started.
Hey, we've got one.
You've got one, right. So we've got a problem we're going to have a look at. So
yeah.
Who knows what question this is, but we'll have a go. It doesn't matter. Right.
Right.
Okay,
so you start with the IR.
Start with the IR.
Nice and simple. And I'll just make it bigger.
Okay, so...
Right. So like as we saw before, there's a peak here.
And that looks similar to what we saw in the previous question,
which is an OH. It's broad. It's you can recognise it. You don't even need to look at the spectroscopy table to tell that's an OH.
Now, what you were talking about in the previous question was that if we had that squiggle above 3000,
so go through all that. You've got a bit of a squiggle here and a bit of a squiggle here. So that lead in that this could be CHs and this could be aromatic CHs. So it makes sort of like, oh, we've got an aromatic somewhere, which is fine. It just means there's more carbon environments to deal with. We'll look at that in the carbon-13. So coming down this way, we've got some things peaking happening here. You saw before 1600 to C double bonds, which is here. There's something happening, but not really recognisable. You've got some spikes here, but they're not really massive.
They're not that significant. When you try to look at these, you're looking at the major peaks all the way down. The ones that are the really big ones that are the signature.
Yeah, anything over 50. Yeah, or depending on if you're looking at transmittance or absorbance, they flip them around the other way just to fool you. But anything above or below 50, 50 is the mark, sort of, whether it's absorbance, which is then anything below, if it's transmittance, everything above, but
so a good place to start.
Good plot. Anything above 50, you want to panic about. So we can see there's some.
So we've confirmed then we've got an OH.
So we've got an
now
OH.
We've got a massive peak at around about 1,000. Now, what's that one?
Now that was looking at the table.
So looking at our table, we've got about 1,000.
About 1,000. Quite a broad peak, not a sharp spike. So about 1,000. Going scrubbly, see if we can find a Fahrenheit. Probably a little bit lower. Maybe on the next page, because there are a lot of pages to go through.
And we're much more at.
There we go, about 1,000. Oh, got a good 1,000 down this way.
Yeah, a lot of thousands
now,
around there.
This is where you use these letters, because S means sharp, M means medium, and
B is going to be broad.
So, looking at the peak on the spectra, that I would classify as a medium broadness.
Okay.
So that if you look back at the spectra, or the spectrum sheet, you can see you're looking now for M's. That's an M, and it's about the right number.
1160, 1050.
Yeah.
It's of the right order, isn't it?
Right order.
So it could be a CO in an alcohol. Okay.
Yeah, right. So we note that down for future reference.
Now, my favourite, look for the carbonyls, the C double bond O. That's going to be around about 1700.
So back on the spectra.
There is nothing there at 1700.
Nothing.
So carboxylic acid is looking
not likely
at the moment.
Not likely. That's
Okay.
fine. Good. Right. So that's all we've got from that. So now let's look at peek at the mass spec, and so we got 100, 110 is the molecular ion, I reckon.
No, a bit less. I reckon it's the 108.
Do you reckon it's 108? Or do you reckon it's 109 is the N+1?
Could be, yes. 108 is a big, massive peak there. 109 is the N+1. I think that at 110 is merely where we've got an extra isotope there counting in.
Yeah, all right.
It's really very, very tiny.
Yeah.
I normally expect to see this N+1 as sort of a little peak, but not that tiny that you've got on there. So I would go for it. It's going to be, I reckon, the 108.
108. So 109 N+1, 108. That's no problem. Right. So now we note 109, and we did say we had a CO bond. So there is an oxygen somewhere in that. So you basically 109 minus 16. Doing a bit of math in my head. I think it's like 94. No.
My maths isn't that bad at trying to do that.
You do tell me what it is then.
Well, we're in the region here of trying to do. You just simply, Paul, you just simply take the 6 from the 9.
Well, that's 3.
Which gives you 3.
I was close 94, 93. It's all right, you know.
It's not that difficult. Right, okay, so we're looking at a number about 93. Now,
so we did see in the IR there was the aromatic hydrocarbons happening. So roughly the benzene, so if I go back to the IR over here,
that was our benzene.
You've got sort of aromatic stuff and you've got some carbon chains. So if you just look benzene, that's 6 carbons.
That's going to be 6 carbons.
And 6 hydrogens. So 6 12s are 72. So you got.
If you want to know how he worked that one out so quickly, I wrote the answer down for him.
Yeah, I know. It's maths. I'm not.
Yeah,
I'm
I know.
A chemist. I'm not.
You're the chemist. You don't do the maths. Whereas you're the expert on doing these
problems.
Well, yeah, you're good at doing these things because you do them sort of nearly every day. Whereas I'm slower at doing these. I don't do them so much, and me, NMR wasn't around much when I was at university trying to do some of this stuff, so right. Makes it harder.
Anyway,
right.
So moving on. So we've got at least 72. So 72 from our 93.
You're looking at
21.
One maybe. Yeah, probably 1.
Probably an extra carbon on top of that.
Yeah, I think probably it looks like 1 carbon extra on here, because that's going to give us, because we've got hydrogens to take into account, so that's the feeling I've got at the moment. Is we've got an aromatic carbon chain, then we will have a carbon there, we've got an OH. Our choices then at the moment is to put the OH on the carbon on this arene, or we can put it onto the carbon chain.
Yeah. So yeah.
There are two options at the moment.
2 options, right.
Can we work out which one of these it's going to be?
Well, let's quickly pop over to the carbon just to check. And oh look, there's your signal about which is the your aromatic carbons. But you have got these other 2, and there, I reckon, there's your single carbon on its own because it's so far down, and I reckon it's carbon number 1, 2, 3, 1, 2, 3 there, and the 4th one there, and that 4th one is probably the OH, and this is where the symmetry of the benzene ring takes a place where you've only got 3, so it's somewhere down the line. There's an OH, and it's just 3.
So we've got confirmation there that we've got a
opposite the carbon hydrocarbon, or the C coming out, there's an OH somewhere.
So we've got our basic 3 symmetry here of 3 and 3, haven't we?
Yeah.
Okay, so and then we've got 1 carbon all by itself, which is, it's just basically this carbon 13 here is confirming what we knew before.
What we knew before, but we're just checking, and we can see where the position of that OH just purely by where it's looking in the spectra, where that symmetry is happening. So that's no problem. That's good. Right.
So we're now off to have a look at our Proton
Nmr. Yeah, glorious. Right. Interesting, they've given us exchange with D2O, and their integral value of 1, and it's exchange with D2O. That means that proton is the OH. That's the OH proton right there.
And it's swapping because it's done in a D2O environment, and that H is just dropping off and being replaced by a D, no problem at all.
So that's on its own. So that's fairly simple.
So we've got an OH all by itself.
That's no problem. Right,
sort
so we
of
come
hung
up,
out to dry.
hung out to dry. So then we got this one, integral value 2, all on its own, far end. That is a CH2, and then you get your 5, which is your aromatic ring, your benzene ring, because that's the 5 with with the C bonded to it. So that's
so
easily.
So we basically got here this this singlet here.
Yeah.
Integration. So we got an integration here of 2. So we got a CH2. So my reckoning then is that's got to be that one.
That's got to be a CH2, and the reason they're all singlets is because they're the same environment. All the protons, they all match the same. You can't tell one from the other. So the M1 rule breaks down because they're all given the same peak, because they're all the same. They look like the same.
Okay.
So
our ideas then, we're getting quite limited what we can actually have as any other alternatives to what I've got. So I'm reckoning on then we've got our benzene ring, we've got coming off that a CH2, and it's looking very likely that we've got an OH
next
put
to it.
onto that.
Yeah.
So I think we're in a position that we can go for looking at the solution.
Right, so 108, that's good, no pattern. We did the OH broad.
So they came up with 108, we came up with 109. So the 109 was the N+1 there.
N+1, yeah, close. You got the broad peak, you got the COO, and there's no carbonyl, which is fine. You got the 5 carbons, 4 of which were the aromatic ones, and you had 2 different ones, which is what we showed. All these, now this is where the quotation of a singlet, because it would be a singlet because they're all the same, but it would be probably more like a multiplet, but you can't tell, it's just one sharp peak because they're the same. But the integration of 5 tells you it's the aromatic ring. D-shielded, this one, yes, it says D-shielded because that's just basically, it's not connected with anything, so it's just pure subject, so that's why it's a singlet N+1. 2 equals 2, so what is 1, which is singlet. And then no H, and there's no coupling because it's the OH. There we saw that, no problem. So we scroll through, and there you go.
So there we go.
And there is only one way you can put that together, which is the important thing. All those facts together, because otherwise you'll be either a ketone or a
So
aldehyde.
we did it all right on that. So we've gone through there 3 to try and give you some idea about how we chat about how to work some of these things out. We could do more, but we tried to choose some different ones. They were at random, and we didn't know what we were actually looking for. My son did give me some rather nice suggestions that we could have a look at, and we had all sorts of lovely ideas that he said, well, we could try some of these, and I thought, well, you having a go at trying to do some of these in the exam, it's probably not likely that you're going to have those sort of things to do. At least we hope not. So we chose to do some, what were called on this website, some simpler ones to have a go at, rather than the more complicated ones. But we worked through, and we tried to give you here some reasoning about why we did what we did and how we tried to choose different ones to try and sort of make some sense of the sort of discussion that's going on, which is why my son decided to join me and dip in, because rather than one person talk about one of these things, starting to discuss these things, especially 2 of you, usually gets a much better response than trying to sort of argue this by yourself. So there we are, looking at IR, looking at NMR, both the carbon and the proton NMRs, to try and work out what we've got, and that with the mass spec helps considerably. We don't use UV so much. That is more for sort of fingerprinting different chemicals. I hope you found this useful. If you did, then please subscribe, and we'll see you next week when we'll have a look at more A-level chemistry topic by topic. Take care. See you then. Bye bye.